Howdy folks, in this video we are going to discuss the QR matrix decomposition and three methods of performing the QR matrix decomposition. We'll demonstrate those all in Python. And as always, all the code you see in this video can be found at the GitHub link in the description, along with some additional written notes and references for the QR matrix decomposition. All that said though, let's begin discussing the QR matrix decomposition. Alrighty, so the QR matrix decomposition is a decomposition of some square A matrix into the matrices Q and R. Q is an orthonormal matrix, meaning that the columns are orthogonal and normalized, and R being upper triangular, which I hope you're familiar with. But the Q matrix is what really gives this matrix decomposition its power and its utility. And that's because of this convenient identity right here. When we compute Q transpose by Q or Q by Q transpose, we get back the identity matrix. And that implies to us that Q transpose is, in fact, Q inverse. And that is a very powerful piece of information that we'll be able to utilize. And basically that is just the QR matrix decomposition. But how can we actually perform a QR matrix decomposition? Well, there are three different methods that we're going to cover in just a moment. But for those of you who just want a quick, easy way of doing this, don't necessarily care too much about the back-end mathematics governing the QR matrix decomposition, here is some pretty simple and easy code that you can, again, find in the description. And we are going to use this numpy Linear Algebra QR function to perform a QR matrix decomposition for the randomly generated 3x3 A matrix that we have right here. We're going to print all those out, and as you can see, it works out the way that we want it to. Our R matrix is clearly upper triangular, and using our Q matrix, when we compute Q by Q transpose and Q transpose by Q, we get back the identity matrix. This randomly generated A matrix we are going to reference with all three of these methods to compare each one of them and compare our results to ensure that we're doing things the way that we want to. And we are going to start off with the Gram-Schmidt process, which uses projections. We'll move on over to computing QR through the use of householder transformations, which is using reflections. And then the last method is using givens rotations. And obviously the transformation method that we'll be employing there is rotations. It's in the name. So let's start off with QR by the Gram-Schmidt process. Now, I have done a whole separate discussion on the Gram-Schmidt process, much more in depth. I'll encourage you to reference that if you need a refresher or you need a little bit more information than what I'm going to provide here, because I'm not going to go too in depth with this particular method. But basically, the Gram-Schmidt process takes some square A matrix and produces an orthonormal matrix for us. The way that I introduced it before is it would take some set of vectors and produce an orthonormal set of vectors, but when we group them all into a matrix, it's really easy, just to see how that all works together. But in reality, when we're working with matrices, we're really just working with sets of vectors. You can think of them as sets of vectors, and that's what the Gram-Schmidt process does. Again, it takes some random A matrix and produces an orthonormal matrix, provided it is square. So then all we really need to do to compute a QR matrix decomposition by the Gram-Schmidt process is just find a way of getting our R matrix. And we can do that really simply here with this pretty simple formula right here, where we're going to compute a whole bunch of inner products between our Q matrix once we obtain it and our A matrix. We can slide them into the respective positions of our upper triangular matrix right here, and that is how we compute a QR matrix decomposition with Gram-Schmidt. But let's review the Gram-Schmidt process very quickly. Remember, again, we're dealing with sets of vectors. You can think of this set of X vectors as our A matrix, the set of Y vectors as our Q matrix. With the first column of that A matrix, we're really just normalizing it and setting that equal to the first column of our Q matrix. Then for the second column, we're subtracting off one projection and normalizing. For the third column, we're subtracting off two projections and normalizing, and this is the way we're obtaining our Q matrix. And I want you to recall here that we're using projections here. We are taking our original set of vectors and we're using these projections to produce a new set of vectors that is our Q matrix. And so here's the code that we can use to perform a QR matrix decomposition via the Gram-Schmidt process. You can see this first function that I have right here called Gram-Schmidt. And what we're doing with it is we're just computing the Gram-Schmidt process, meaning that we're doing those projections, we're doing those normalizations, and as you can see, we are returning that Q matrix we get right at the end. So in the second function here, QRGS, that stands for QR by Gram-Schmidt, we're accepting some A matrix right here, that randomly generated A matrix that I showed you from before. We're getting, the first thing we're doing is we're getting the shape of that A matrix, which should be square. We're generating our Q matrix with our Gram-Schmidt function second, and then we are generating a matrix of all zeros. And in these two loops right here, we are computing all the necessary inner products and sliding them into the respective positions from this particular formula right here that I showed you before. More particularly, inside this first loop, we are taking care of the inner products along the diagonal of our R matrix, and then the second loop is taking care of everything above the diagonal. Alright, this is the result that we end up getting. You can see I'm computing a runtime, and we're going to compare the runtimes using each one of these methods right here, but you can see that our R matrix is clearly upper triangular, and we're not going to compute Q transpose by Q or Q by Q transpose, but we can compare it to the results from before using the numpy lin alg QR function, and you can see, comparing each one of these results, that our R matrix is almost identical, except we are differing by a few different minus signs, and that's perfectly okay. So long as the absolute value of each one of these numbers is there, that's what we want. And you can see the same thing for our Q matrix. I'll encourage you to pause it and spot check this if you want to. And again, if you want to audit all the code to make sure that this is actually working and compute A minus QR, you could go ahead and do that, and you'll find that you end up getting the zero matrix back out, so everything's working out all right. Alrighty, so the next method that we're going to discuss for computing a QR matrix decomposition is through the use of householder transformations. And I'll forewarn you quickly that this method, at least for me, is not necessarily straightforward. So let me explain what we're going to do more generally, and then we'll dive into the details of it as we go through the code. The way that this process is going to work is we're going to compute a series of QN matrices right here, and we are going to matrix multiply them all together, then multiply that product by our A matrix to get our R matrix. But we're going to be computing Q1, Q2, Q3, multiple different QN matrices, and then taking the product of all those together. Then what we can do is we can just transpose this to get our actual Q matrix, because remember, A is supposed to equal QR, not QA is supposed to equal R. And so we're just going to transpose all those, and so we're going to have Q1 transpose, Q2 transpose, all the way up to Qn. And so I know this might be a little bit confusing right now, but just know that we are going to be computing or generating these different Qn matrices, getting a product of all them together, and then doing what you see right on the screen as a means of getting our R matrix. Now, before we discuss this any further, the key benefit of this particular method over the Gram-Schmidt process is enhanced numerical stability. Now, that's not something that I've discussed here on the internet yet, and that's certainly something that I should at some point in the future. But for those of you that do know what it is, I just want to throw that out there. For those of you that don't, just know that there is a benefit over Gram-Schmidt, but we'll certainly discuss numerical stability sometime in the future. So with Gram-Schmidt, we used projections, recall, to get our orthonormal matrix or our Q matrix in this QR matrix decomposition. Well, with the householder transformations, we're using reflections, and that's going to show up right now when we go through this code. So this is the function I've written to compute a QR matrix decomposition through the use of householder transformations, and I think it's going to be best to understand the mathematics by translating this code into the mathematics, and you see in that firsthand right there. So in these first few lines, you can see right here, we're getting the shape of our A matrix. We're storing a copy of our A matrix as our R matrix, and we're setting our Q matrix, which is going to end up being the complete product of all of our QN matrices, but we're going to first set it as our identity matrix. And so this is what we're going to be going for first. We're going to be looking to get a Q1 matrix in this particular configuration, but we're going to start off with that Q1 matrix being the identity matrix. Then as we change that identity matrix and matrix multiply all the different Qn matrices by that identity matrix, it's going to change our R matrix. And so really, as we change one side, it's going to change the other, and that's exactly what we want to have happen. And you'll notice that we only have one loop in this function. This is looping over all of the columns of our A matrix, except for the very last column. And you'll see why that's the case in a moment. But then we have these 4 lines right here. Now, what are all these 4 lines doing? Well, let's translate that to the mathematics, and it might make a little bit more sense. What we're doing is we're establishing this U vector right here. And we're doing that with different vectors of our R matrix, which in this case is really just our A matrix. So for the first iteration, or for Q1, we're really using the first column of our A matrix. Then we're going to subtract off a vector of all zeros with the exception of the 2 norm of that particular column put in the first position of that vector. And that is what all 4 of these lines are doing. The first thing that we're doing is we're getting that 2 norm, setting that equal to alpha. This AVEC line right here is just establishing a vector of all zeros. The third line here is just setting that 2 norm into the first position of that vector of all zeros. And then we are just performing that vector subtraction that you see right here, again, for this first column of our A matrix, but in reality, it is our R matrix, because once we go to compute Q2, our R matrix is not going to be equivalent to our A matrix anymore. So then we have this line here for V, and this next line here called Qn. What exactly is going on here? And so at this point, our I matrix is no longer really there. Our R matrix is going to completely change, and we're just going to be dealing with this Q1 matrix and getting this Q1 matrix, which is going to change our R matrix. So our R matrix is not going to be a copy of our A matrix anymore. And so we have our U vector established from the previous 4 lines, and all we're doing with that first line that I showed you is we are normalizing that U vector and calling that normalized U vector V. Then what we're going to do to compute our Qn matrix is just take the identity matrix and subtract off 2 times the product of our V vector by our V vector transpose. So V by V transpose is going to produce a matrix for us. So we're going to take the identity matrix of the same size and subtract that off. That's going to be our Qn matrix. And so the normalization is just the first line. That identity matrix minus 2 times V by V transpose is just the second line. Alrighty, so this next line is a little bit confusing. It's going to come up when we go to compute Q2, so we'll touch on that more in a moment. But this R line right here is just updating our record for our R matrix by computing Qn by R. Then we're just updating the record for our Q matrix by computing Q by Qn transpose right here, which is going to keep track of the transpose, and it's just going to keep track of the full product of all of these Qn matrices transposed. And so what you'll see at this point is that for our R matrix, the first column is going to have everything zeroed out below the diagonal for that R matrix. And that's what each one of these Qn matrices does, is it will zero out everything below the diagonal for the nth column of our R matrix. So when we compute Q2, we're going to be working with this submatrix. We'll get to that in a moment, but we're going to be zeroing out everything below the diagonal in this second column. And that's why we need to iterate over every single column of our matrix, with the exception of the last column, because with that last column, we're not going to need to zero anything out below the diagonal. To compute Q2, we're actually going to use this submatrix right here, which is of smaller dimension. We're going to repeat all these same steps right here, but we have a problem. This submatrix right here is 2 by 2, and all the other matrices that we're dealing with are 3 by 3. In order for us to perform proper matrix multiplication, we're going to need to fix that. And that's what this line that we skipped over from before actually does. What this line does is it takes this product right here of the submatrices and it pads it with ones along the diagonal and zeros everywhere else. This is going to actually allow us to perform all of this matrix multiplication to get our cumulative QN matrix back out. Now, to get a better understanding of what's going on with here is the Jupyter Notebook with all the code and the references and the additional notes. And what I'm going to do is I'm going to quickly go into this function right here for QR by householder, and I'm going to add in some print statements, and we're going to rerun this with a different randomly generated A matrix so you can see exactly what's going on right here. And so the first thing that I want to show you is I want to show you what's happening with this QN matrix. So we're going to add two print statements right in here for the identity matrix minus 2 times V by V transpose. And then I also want to print the same matrix out after we do this blocking in here. After we do this padding with ones along the diagonal and zeros everywhere else so we can actually perform the matrix multiplication. So here we go. Here you can see we have a 3 by 3 matrix right here. It's the same 3 by 3 from before. We don't need to pad anything because it's 3 by 3 and it all works. But when we compute Q2, which is right here, Q2 is 2 by 2 because we only need it to zero out, because we just need it to zero out everything below the diagonal of this second column. And so it's a 2 by 2. We're not going to be able to compute the product of a 3 by 3 and a 2 by 2. So we pad it right here with a 1 along the diagonal, zeros everywhere else, and it all checks out. Now there's one more quick thing that I want to do with these print statements right here, and that is I want to show you what's happening to our R matrix with each iteration. There's only 2 iterations because this is 3 by 3, but we're going to print out our R matrix as we iterate through. And so you can see here is our R matrix after the first iteration, and I want you to notice that these values below our diagonal are on order of 10 to the negative 16. We can effectively round those to being 0, although right here we still have a full value. Upon a second iteration, though, you can see that these values are still on the order of 10 to the negative 16 in the first column of this R matrix, but below the diagonal in the second column we have a value that is now on the order of 10 to the negative 17. Again, we can round that to be 0. It's effectively zeroed out, and that's what's happening down here when we actually print out our R matrix. Okay, and again, you can find all of that code linked in the description. I'll encourage you to go play with it. It's a Jupyter notebook, so it should be really easy for you to run and just play with and experiment with. Add in those print statements. It's really helpful, but this is the final function that we are using to compute QR by householder. And now if we compare our results with the old randomly generated A matrix, and we compare that to that of Gram-Schmidt, you can see that all these values are exactly the same. But notice that by householder, to perform this same QR matrix decomposition, it took 908 milliseconds compared to 552 milliseconds via the Gram-Schmidt process. And so although the Gram-Schmidt process is faster, a lot of people prefer to use householder because of that enhanced numerical stability. Now again, I haven't discussed that in depth with you guys. It's something to do for a future video, and it's certainly something important enough that it should merit its own video. But that brings us to the last method that we can use here to compute a QR matrix decomposition, and that is through the use of Givens rotations. Now, Givens rotations is actually developed by Givens, and that's why it's called Givens rotations. This individual is someone who particularly focused on numerical or computational mathematics, and so it's really designed to kind of give you the best of both worlds, and to be quick and also to have good numerical stability. And so we're going to follow a very similar general procedure to householder, except these are rotation matrices now, not dealing with reflections or anything else like that from before. Each one of these GN matrices is not going to zero out an entire column below the diagonal like what happened with householder, but instead it's going to zero out one matrix element below the diagonal at a time. So we're going to actually need to find more of these Gn matrices than Qn matrices with householder, and that might seem a little bit weird. We need to find more matrices, so it should be slower, right? Well, not quite, because the two benefits, as I already mentioned from before, is enhanced numerical stability. Again, we'll have a conversation about that in the future, but we're going to get increased computation speed, and you'll see that here in a moment. And so when we take a copy of our R matrix like we did from before, we're going to need to compute Gn matrices to zero out this A21 value, this A31 value, and the A32 value to get to that upper triangular form. Let's see that in some action and break down the code. But before we do that, recall with Gram-Schmidt, we're using projections as a means of generating our orthonormal matrix or our orthonormal set of vectors. With householder, we were using reflections to generate our orthonormal matrix, or again, orthonormal sets of vectors. And then with this last method here, we're using rotations. And so we're doing very, very similar things to get to the same result, but the way that we're going about doing it is just slightly different. And there are benefits and pros and cons to each of these. And so it really does pay to understand your transformations. You'll see that in a moment. But before we can actually use Givens rotations, we need a quick refresher of our trigonometry, because that's going to be the key factor in doing this decomposition with Givens rotation. So here you have a right triangle, A, B, and C right here. You'll recall your Pythagorean theorem, hopefully, a squared plus b squared equals c squared. And then, of course, your relationship for sine and cosine for this right triangle right here. We're going to utilize all of this knowledge right here to perform this decomposition. And we're going to do that with rotation matrices. Here is a 2x2 rotation matrix using sines and cosines. The same sines and cosines that you see right here for this right triangle, okay? And you can see that also in 3 dimensions for x, y, and z also. Going down the whole rabbit hole of rotation matrices is interesting enough in of itself, but I'll leave that for you to do. Here are just what some of these look like. And here's the code that we're going to use. You can see again we have 2 functions. And this first function here is accepting an a scalar and a b scalar, just like you saw from before with regards to our right triangle here. And that function is going to produce our sines and cosines that we're going to use to do the decomposition. And so with this function right here, the first thing that we're doing with a and b is we're computing our hypotenuse using Pythagorean theorem. Then we're getting our cosine, and then we're getting minus a sign. We're returning both of those. I will note here, though, that if you go ahead and check out a bunch of the references, this is actually an incomplete function. This function will actually run into some problems mathematically for you. I'll leave that as an exercise or an extracurricular exercise for you to do. It's actually pretty interesting, but I'll just give you a quick hint here, and I'll say think about discontinuities. Moving on to the second function, QR givens, which accepts our A matrix. You can see we have effectively the same setup as we used to set things up for householder. This is effectively what we have. Instead of our Qn matrix, we have a Gn matrix, which is G1. That's originally going to be our identity matrix, and as we change the values of our cumulative G matrix, we are going to go ahead and be changing the values of our R matrix as we go along. And then we're just going to transpose this product of all these Gn matrices as a means for us to get our Q matrix, just like we did with householder. And so let's actually break down this code right here, because there's a lot less of it, but it's a little bit more confusing, and it's certainly not PEP 8, as 2 of these lines are very, very long. That's more of something for you Python programmers out there. But anyways, we have these 2 loops right here, and you can see that we're doing one right after the other. This first loop is looping over our columns. The second loop is looping over our rows. The first thing that we're doing is we are getting our sines and cosines, plugging in different values of our R matrix. Let's take a look at what those values actually are. So here we have our A matrix, which again, for our first Gn matrix, is just going to be the same as our A matrix. These are the 2 values we're going to be plugging in. We're going to be plugging in our value that's along the diagonal, and then the value below the diagonal that we want to be zeroed out. In this case, it's A21. We're going to compute our hypotenuse using A11 squared plus A21 squared is equal to C squared. And then once we have that, we can use both of these values to compute sine and cosine. Sine is going to be a21 by our hypotenuse, and cosine theta is going to be a11 by our hypotenuse. Then what we're going to do is we're going to take those sine and cosine values, and rather than actually compute a Qn matrix, we're going to plug them into these two long lines right here. And these lines are very confusing, so let's look at them one at a time in depth. The first line is only strictly changing the rows of our R matrix. We're going to be setting the ith row of our R matrix equal to that same row times cosine theta minus the jth row by sine theta. Then we're going to do something very similar, but just swap things around. We're going to set the jth row of our R matrix equal to the sum of our ith row by sine theta and the jth row by cosine theta. These are all just scalars multiplied by the rows of our matrices. We're not doing any particular matrix multiplication. The important bit with this is that both of these need to execute at the same time. That's why you see them in the same exact line of code, split by a comma. We're going to do a very similar thing with our Gn matrix, which I've left the variables as Q from householder, so hopefully that doesn't confuse you. In hindsight, I should have changed it to G, but in any event, we're doing effectively the same thing, but we're doing that with the columns of our G matrix, or in this case, Q. We're going to set the ith column of our Q matrix equal to the ith column by cosine theta minus the jth column by sine theta. Then for the jth column, we're going to set that equal to the ith column of our Q matrix by sine theta plus the jth column of our Q matrix by cosine theta. And again, these need to execute at the same time. That's why in the code right here, you see them again, all part of the same line. So although these lines are much longer, it is necessary, okay? And we're doing that for each one of the elements that we need to zero out below the diagonal for our R matrix. And so to compute G2, we're going to be plugging in A11 and A31 because we need to zero out whatever value is in that A31 position. So we're going to then compute our hypotenuse with Pythagorean theorem. We're going to go ahead and generate our sines and cosines, and then we're just going to put them through this same process, except with the different sines and cosines. Then we're going to also need G3 here, but G3 is going to be to zero out A32, and so we're going to pass in the next value along our diagonal in order to do that. So it's going to be A22 squared plus A32 squared is equal to our hypotenuse squared. We're going to get our sines and cosines, and again we're going to put it through this process here of just multiplying rows and columns of our matrices by the sine and cosine scalars. And so when we take a look at the results, that's what gives it this really fast processing time of 230 milliseconds. Again, compare that to householder, we have 908 milliseconds. So Givens is much, much faster, and again, we still get the benefit of enhanced numerical stability. But it's even faster than Gram-Schmidt as well. Again, check out all the values. They're all exactly the same, because this is all for the same randomly generated A matrix. But back over here in the code, I want to just quickly go through and add in the print statements again, just so you can see what's going on right here. What I want to do right here is I want to print out that R matrix for you so you can see what's happening with each one of these iterations that we're doing. We only need 3 of them right here because we're only doing a total amount of iterations for the amount of values we need to zero out below our diagonal. So let's print out our R matrix. And you can see right here we have 3 different matrices in the terminal. The first matrix has this R21 position zeroed out. Then we have that R21 position zeroed out from before, along with, below that, a value on order of 10 to the negative 16, and we can effectively just round that to being 0. Then again, you can see right here, for this R23 position, we have 0. And that's exactly what we want. We need 3, so we need 3 different iterations to go through and do that for this 3x3 case. And again, just as a check, you can see that both of these are identity matrices, for Q by Q transpose and Q transpose by Q. The other thing that we could do also, and you can see it's all just a zero matrix with two values that are very close to zero. Again, we could round those just to effectively be zero. So everything for this code checks out. Again, you need these lines for R and Q to work. But who would have thought that the method developed by somebody who had numerical mathematics or computation in mind would develop the most efficient method as a means to do this? And so before we close out, I just want to touch on some of the key benefits of the QR matrix decomposition. I don't want to focus too much on these benefits as they're going to come up in future videos when we utilize our knowledge of the QR matrix decomposition. But so far throughout all the conversations I've put up on the internet for linear algebra, we've been discussing solving these linear systems. And the QR decomposition definitely helps with that, because we can use two different decompositions as a means of solving such a linear system, provided that A is square. Before, we could use a LU decomposition, but now we can also use QR. And it's very simple to solve this linear system using QR, because we need to isolate our upper triangular matrix as a means to perform Gaussian elimination, and in order to do that, we just need to get the transpose of our Q matrix, put it on the other side of our equation, do some matrix multiplication, and we're done. However, with our LU decomposition, we have to actually go through and fully compute the inverse of our lower triangular matrix. And there's a reason why I haven't particularly done any conversations or videos specifically on the topic of matrix inverses or computing matrix inverses, and that's because it's not necessarily the most straightforward. We'll discuss something called the pseudo-inverse, which is a lot of times what is happening when you're computing a matrix inverse. And so this is just one key benefit right here, and it's something that I can tie back to all the different conversations we've had so far, particularly with regards to solving linear systems. We're going to use QR to compute eigenvalues and singular values, which are incredibly important in their own right. In my background in physics, you need to understand eigenvalues, so any of the physicists that are watching this, I mean, eigenvalues are important. They're important in a lot of different applications, but more particularly, QR is going to be seen a lot in machine learning and AI type use cases. It's going to be used in things like compression algorithms. So folks, that is the QR matrix decomposition and the three different methods of how we can compute the QR matrix decomposition. If you have any questions, comments, or concerns, don't hesitate to let me know. Hopefully this helped you out in your understanding of the QR decomposition. It's, again, incredibly important and incredibly useful. We're going to use it a lot in the coming videos I have planned. But I want to thank you all very much for watching, and I'll hope to see you all again next time when we'll discuss some more linear algebra or astronomy or astrophysics or physics or whatever the heck else I happen to want to make a video about. But again, thank you very much for watching. I hope to see you again next time.